and welcome to the first lesson on differentiation. So before we go into differentiation proper, there is a concept that I need to explain, and that is limits. So I feel a lot of students gloss over this concept very quickly, and what results is that they think or they feel that differentiation is about memorization of rules, right? I feel that if you take time to understand limits a bit more, to see the genius behind limits, and then you will definitely look at differentiation in a different perspective, right? You'll come to understand how beautiful the concept of differentiation is. So without further ado, let's go into limits. Right, here are the notes, and on the right, you'll see a checklist of certain points, 4 points today that I would like to go through, which will help you understand limits a lot better. Okay, so right off the bat, you see two guys on the front of the notes, right? Who are they and why do they have long hair? I will give them a proper introduction in the next lesson when we start on differentiation proper. But until then, yeah, it's just a surprise for you. Okay, so for some of you who have already started learning differentiation, you might have heard the phrase before. Let me write this down. Okay, it's in blue, which means that you need to write this down as well in your notes, right? Taking limits as, say, a certain alphabet, which we like to use most of the time, H, approaches 0. Okay, this is something you might have heard many times your teacher saying. You might have no idea what it means, right? First thing you might wonder to yourself is, what are limits? And second, why do we approach 0? Why can't we just go to 0 or be at 0, right? So let me try to answer that. But first of all, we need to look at a number pattern, So this is a simple number pattern I'm sure you've seen before, maybe in P6 or maybe even in Sec 1 when we studied number patterns. The first pattern is just 1. The second pattern is 1 plus 1. The third pattern is 1 plus 1 plus 1. And if you go to, say, pattern number infinity, right, we get 1 plus 1 plus 1 infinitely many times. So the question here is, what is the value, what is the sum of pattern number infinity, which is t infinity? What is that? Because I know the value of pattern number 1 is just 1. Pattern number 2 is 1 plus 1, that's 2. Pattern number 3 is going to be 3. What is this equals to? I think many of you can guess this, right? The answer is infinity. But why? So some of you will say this. Oh, we just keep adding and adding. If you keep adding, then of course you'll go to infinity. Yeah? Okay, I kind of agree with that. So we can say this. Let me just write this down very quickly. As the number of ones. Yeah, so these are the number of ones over here. Number of ones. Okay, as the number of ones approach infinity, the sum approaches infinity. Okay, so again, you see the word approach, right? So you might have some idea why we use the word approach, but let me just go through another example before I explain why we use the word approach. Okay, you'll truly understand in this next example. So let's look at another simple number pattern, right? In this case, pattern number 1 is just half. Pattern number 2 is half plus 1/4. Pattern number 3 is half plus 1/4 plus an 8. Yeah, so you would guess pattern number 4 will be half plus 1/4 plus an 8 plus 1/16. Yeah, okay. And then again, the question is, what is the value of the pattern number infinity? Yeah, so if I keep adding on, plus a 16, plus a 32, 1/32, 1/64, 1/128, so on and so forth, infinitely many times, what would I arrive at? Okay, so many of you will say that, hey, isn't this the same question? We're just adding things infinitely, right? If I just keep adding and adding, you'll reach infinity, of course. Well, I've got some news for you. In this case, it actually doesn't go to infinity. Yeah, it doesn't. So you'll see over here on the right-hand side, it's a picture of me saying, hey, you know what? In this case, no, I don't agree with you. Let me explain why. Okay, so you know what? I'm going to get you to look at this frog. Yeah, here, let me introduce you to a frog. Okay, this frog is starting from, it's on the number line. Yeah? It's on the number line, it's at 0. Okay, his goal is to reach the end over here. This is his goal. Oops, sorry, that's a bad arrow. Right, his goal is the number 1. He wants to reach there. But this frog is a bit special, right? What he does is that he always jumps half the remaining distance. Half the remaining distance. Okay? So as of now, he's starting at 0 and he wants to get to 1. The remaining distance is 1. So he will jump exactly half. He'll jump exactly half. So I'll say that he'll jump here. That is half. Okay, that's what he does. So let's move this frog here. It's now at half. Okay, and let's look at the remaining distance now. So what is the remaining distance he has to the goal? And you can see it's half. What is half of a half? It is a quarter. So the next jump, he will jump 1/4 here. Okay, and I'm going to move this frog here. There you go. It's now at 3/4, 0.75. Okay, what happens if he wants to make another jump? He will have to jump half the remaining distance. The remaining distance is a quarter, and half of that will be an 8. So he'll jump 1/8 the distance. Okay, and you'll see that he moves here. So my question is, what is the remaining distance? It is 1/8, and his next jump will be 1/16. Yeah, and then the next one will be 1/32, 1/64, 1/128, 1/256, so on and so forth. Okay, I've got questions for you. Number 1, will this frog reach infinity? Apparently not. You can see, right? He's never going to reach infinity. If he's not going to reach infinity, where will he end up? Okay, so I know a lot of students will say, of course you'll end up at 1. But if you think about it, think carefully, right? He doesn't actually reach 1. This frog will never reach 1. You'll get really, really, really close to 1, but never reach 1. Yeah? Because he always jumps half the distance, half the distance, half the distance, so on and so forth. Okay? So I want to write this down. Okay, now we can truly understand the meaning of the word approach, because it's about being really near, but not getting there. So we say as the number of terms, right? We're not adding ones now, we're adding fractions. So the general name of these fractions are just terms, right? As the number of terms approaches infinity. Right. This number of terms will be infinite, right? The sum approaches 1. Okay, and I want you to take note over here. Yes, it approaches 1, meaning what? It will never get to 1, right? It never, or the frog never actually gets to 1. It never actually reaches 1, but it's really close. Right? Okay, so that is what I mean by approach. So you see another approach here, approaches infinity, right? That also gives you an idea, right? Infinity is somewhere that we will never arrive at. It's not a number, right? It's a concept of a really, really huge number that you will never reach, right? If you say infinity is 10 million, then I'll say that, what about 10 million plus 1? And say, okay, 10 million and 1, I'll say, what about another plus 1? And you keep adding and adding and adding, and we will never reach, right, a number that is infinity, right? We can just keep going on and on. Okay, so we also approach infinity. We never get there actually. Okay, so with this, I think I've answered the question on the checklist, right? Adding infinite numbers will get us to infinity. No, that is not true, right? That is not true. I've also answered the question about approaching, right? Approaching means that we are getting close to somewhere, but we're never actually getting there. Yeah, we're getting close, but never actually reaching the destination. All right. So with that, I want to move on to the notation and language of limits. Because as you study mathematics, you have to write, you have to read, you have to ask questions. Of course, you need to learn how to write it or learn how to say it. Therefore, you can exchange ideas, you can ask your teachers, you can do practice questions. Okay, so here's just a quick revision. Right, since we'll never arrive at where? At infinity. We can only approach it. We can only approach it. So in mathematics, we approach by taking limits. So taking limits, right, is like saying that we want to get near a certain point and see what happens. Like the frog. What happens if we jump infinitely many times? What's the number that we get to? Yeah. So we write this as taking the limit, right, of say a function. So how we write that down is we first write a LIM. LIM is a short form for limits. And below the three letters LIM, you actually see H, an arrow, and infinity. Yeah, so this tells us that we want to approach, we want to find out what happens when H approaches infinity. And then we write whatever that we're interested in, a function, for example. Okay, so for example, if, just a quick one, say if this function is just H plus 1, okay, meaning that when H equals to 1, I get 1 plus 1, H equals to 2, I get 2 plus 1, you know, H of 1 is just 1 plus 1, H of 2 is 2 plus 1, H of 3 equals 3 plus 1. And then I want to know what happens when I put H of infinity in. What would I get? Yeah, this is what I mean by taking the limits of f of H. Okay, so next, I'm going to tell you how to read this thing. How to read this thing over here. To read this, we say taking limits of, oops, you know what? I should use green. Okay, this portion here, please change it to green. Oops, what have I just done? Not what I wanted. Okay, this will do fine. Change this to green. No, this is not the green. Green. Sorry, just let me look for the green that I usually use. I think it's this one. Yeah. Taking limits of the f of h. F of h. Again, back to green. As h approaches infinity. Okay, so you realize that it is really quite a mouthful, taking limits of the function as h approaches infinity. This is how we read it. Yeah, and mathematicians are famously lazy, right? We have managed to reduce a long sentence into just kind of like 2 words written in the notation, right? Just lim and f of h. Yeah. Okay. So with that, I would also like to check off the second checkbox, the notation and language of limits. Right. There you go. So now that we know what it is about, how to write it, how to read it, let's do some practice questions. Let's take limits, right? This time. Okay. So over here, I have a function in terms of h. It is 2h plus h squared over h. Okay. And I'm interested to find what happens to this function as h approaches 0. So it's over here. Yeah. So it's over here. This thing over here. Right, so again, to read this in proper, I'll say taking the limit of this function as h approaches 0. Okay, so right off the bat, I know a lot of students will think like, okay, if h approaches 0, why don't we just substitute 0 inside here, right? This will be 0, this will be 0, this will be 0. Yes, easy. We sub h equals to 0. What is the problem with that? The problem with that is you end up with 0 over 0. Okay, and you see a very angry Mr. Wu at the bottom, right? Please write down. That's a no, right? We don't substitute h equals to 0 because dividing by 0, right? Can you see that we end up with a division by 0? Dividing by 0 is a big no-no in mathematics. Okay, I might have run through this with you before, why dividing 0 gives us a non-answer, right? It's undefined, okay? In fact, you can also use limits, right, to reach the conclusion why it's undefined. Okay, so but for now, just know that don't divide by 0 ever. Okay, now, so what do we do then if you can't substitute h equals to 0? Okay, so instead, I want you to imagine h as a really, really small number, right? Instead, imagine h is a very small number. For example, you can think of h as 0.0001, 0.0001. Okay, so what happens? I can divide by 0.0001, okay, 0001, to the top, to the denominator and the numerator of the fraction. Yes, I can divide by h throughout the fraction. So what that gives me is this. Taking the limits as h approaches 0 of this fraction, 2 plus h. Okay, and remember, h is really, really small, right? 2 plus 0.0001 is pretty much the same as just 2, right? It's pretty much the same as 2. Okay, we can safely say that this is now equals to 2. Okay, let me give you some examples of why we can ignore 0.0001. Say if you're doing, okay, I'm going to talk about the science subjects that you do in school. For example, physics, right? In the lab, you measure the period of oscillations, maybe 10 oscillations of the pendulum, right? Doesn't really matter if the reading you get is 13 seconds or 13.0001 seconds. Doesn't really matter, right? Or let's say in chemistry, when you do titration, right? When you're doing titration, does it matter if the amount of, I don't know, phenolphthalein that you drip into your measuring flask? Sorry, it's been a long time since I did chemistry. Right? Doesn't matter if it's 13 milliliters or 13.0001 milliliters. Doesn't really matter, right? Or let's say in biology, right? If you cut a strip of potato and you put it in water, you want to measure how much the potato strip is growing by. Doesn't really matter if the length increases by 0.1 cm or 0.0001 cm, right? No, it doesn't really matter, right? Sorry. Does it matter if it increased by 0.1 cm or 0.10001 cm? No, it doesn't, right? So sometimes the numbers are so small, they are negligible. We can ignore them, right? So that's what's happening in this case. We say that the answer is 2. The answer is 2. Or rather, okay, the answer is not 2. We can say that taking the limits, we arrive at this value. Okay, but I want you to remember, just like the frog, right? The frog actually never reaches 1. We are saying that after taking limits, right, we are not saying the answer, okay? We're not saying this. So the answer is not 2. We say it approaches 2. Yeah, but then it is so small. It's so small, right? Like the frog. It's so close to 1. We just consider it as 1. Yeah, we just consider it as 1 when we take the limits. Same thing here. It is not exactly 2, okay? But we're going to say it's 2 after we take the limits. Okay? Yeah, so I'm going to check off the box on the right-hand side, right? Taking limits is not about substitution. It's about putting in numbers that are really, really small and very, very close to the number that we want. Yeah, like instead of 0, maybe I put in 0.0001. Instead of infinity, I can put in numbers like 99999. Or negative infinity, I can put negative 99999. And then we can see what happens over there. Yeah. Okay, good. So that's one example of taking limits. I want to go through another example. Right? Here's another example. Okay, we're taking limits of this horrendous looking thing over here. So what I'm going to do is I'm going to write this in a nicer form. So let's take the limits as h approaches 0 of this function. I'm going to write a big bracket because I don't want to write 2 layers. I'm just going to put a divide by h over here. I'm going to remove the denominator and write it separately as a divide by h. Okay, so what do we want to divide by h? This thing here, 1 over x minus h minus 1 over x. Okay, and we know how to do this. Okay, I'm going to handle the inner brackets first. We're going to do this divided by h. This will be x minus x plus h over x into x plus h. Okay, and you realize that this thing over here, x minus x is just 0. This just becomes h. And if I take this fraction and divide by h, I can cancel this and cancel this. So that means my fraction is just now, my fraction will reduce to this 1 over x into x plus h. Yeah? Okay? Right, so if you don't have enough time to copy down this, you can just pause the video. I'm going to move ahead to the next page, yeah? The next page. So, this is x minus h. I think I made a typo. Yeah, sorry, this is minus, isn't it? Minus, sorry, huh? For those of you copying, please take note, this is a minus. Very sorry about that. Okay, so we ended up with this thing over here. Yes? And then we say that, okay, in order to proceed further, we imagine h as a really small number, right? So remember, Mr. Wu said this before. Don't worry, just imagine h as a really, really small number. Okay, but this guy asks, hey, but what happens if x is also the same kind of very small number, right? Small number minus small number means that this one becomes 0. Then how? How do we continue with this? Okay, this is where we appreciate the beauty of limits. In that case, then we can make h even smaller. Yeah, we can let h equals to 0.000000000. We can put twice the number of zeros, as previously. We let it be that, yeah, so that it becomes negligible again. Yes, because when we approach 0, we can go infinitely small, right? We can go infinitely number of zeros before we put a 1, right? 0.001. Okay, and then that makes, right, h negligible again. Yes, so I think this concept is really, really beautiful, right? Okay, so I think these two people, by now you should know, they are the two main people who are credited for the invention of differentiation. Okay, so let's take some time to appreciate the beauty, right, of approaching 0 endlessly, right? That allows us to always make h negligible compared to whatever that function that we have. And therefore, we can find the limits of something. Okay, we roughly know the position of it, although we can't say for sure, right? And that is the beauty of limits. Okay, so with this concept of limits, you should be able to understand the next video when we talk about differentiation. And yeah, I hope this video has been helpful. Thank you for watching, and I hope to catch you in the next video. Cheers.